Moving on to the next section, 2.3, centered vectors and variances and covariances of vectors. So what we're going to do is state a whole bunch of formulas, recall some formulas from introduction to statistics, elementary data analysis, and try to sort of encode these ideas of data, means, standard deviations, variances in terms of vectors and vector equations. Okay, so that's the plan. We'll treat in the notes based on the book's results, we'll treat vectors as if they were data sets. We'll primarily treat them as if they're samples from a population, but let's start out actually talking about some population parameters. Recall, if x1 through x sub n are data points from a population of size n, then the mean of that population, mu, is the sum of those x values divided by the number of those x values, the sum from I equals 1 to n of x sub I divided by n. The variance measures, in a sense, sort of the spread of the data, usual stuff, about the mean. So we take x sub I minus mu squared for each value of I, sum those up and divide by n. Usual definition for variance of a population represented by sigma squared, where the standard deviation, sigma, is the square root of that quantity. Now, we'll primarily deal with this from a perspective of a sample from a population, a sample of size n, in which case we have x1 through x sub n as data points sampled from a population. I don't know the population size, I know the sample size. Then we have the sample mean, x bar, being the same as what we had above. We'll sample those values and divide by the number of values. Sample variance, this time as a sample, we'll divide by n minus 1 as opposed to n when we had the population values. And similar type thing to the population variance, but we'll take x sub I minus x bar, as computed above, squared, sum those up, and divide by n minus 1. And as similar to above, for the sample standard deviation, we'll take a square root of that. Represent, there's notational differences between populations and samples. So we've got mu and x bar for the means, be they population or sample respectively, sigma squared and sigma versus s squared and s for variance and standard deviation, whether they be population or sample. Okay, but what we'll deal with here, and the only real significant difference is this stuff in terms of the n minus 1s. We're dividing by n minus 1 in terms of variance and standard deviation as opposed to n. So what we're looking at is inspired by thinking of a vector x as containing a sample of a population. So the coordinates correspond to values of some quantity in that population. All right, for given n vector x, its centered counterpart we'll denote by x sub c. It's defined to be x sub c equals x minus x bar. Here we're treating x bar, and a little notational weirdness based on this. We're interpreting x bar to be the vector, the n vector, each of whose components is x bar. So indeed, we've taken x, think of it as a vector of data, we've subtracted x bar from each of the components. And you can see how we might be interested in this quantity in terms of calculating variance, for example. But x sub c will be defined as the vector. X sub c equals the vector x minus the vector x bar. If we were to take the magnitude of this vector x bar, we'll square all the components, add them up. That'll give us a total of n times x bar squared. Take a square root if we want the norm. So anyhow, the norm squared of x bar is n times x bar squared. Time for me to complain about notation. Okay, so on the left-hand side, that x bar indicates the vector as given over here. How can you tell? Because we're taking a norm of that x bar. And here, we've got a norm squared, so this would have to be a scalar. Here we've got n times x bar squared. So this x bar is the x bar is the x bar computed above. So this is the sample mean, if you like, whereas this x bar represents a vector. Clear from the context, as they say. Yeah. I wish they'd use different symbols for vectors and scalars in general, but in particular for x bar and x bar. Remember, we're using x bar to represent this vector, and we're using x bar to represent that mean, that sample mean, which is a scalar. Any vector for which the entries, the coordinates, sum to 0 is called a centered vector. We'll do some computations where we find centered counterparts. I won't really encounter this more general idea here. But what we want to do is express means, standard deviations. We'll also look at covariances and correlations, and express those in terms of vectors. In one of the exercises, it's shown that the centered counterpart of vector x plus vector y is equal to the centered counterpart of vector x plus the centered counterpart of vector y. So this centered counterpart thing behaves in a linear sense in terms of vector addition. Also, we can interpret x bar the scalar, or x bar the vector. Let's see. We can interpret x bar as a projection. Okay, projections are vectors, so yeah, we must be talking about the vector x bar. We can interpret the vector x bar as the projection onto the 1 sub n vector of the data vector x. Remember 1 sub n, the vector, the n vector, all of which components are 1. So the vector 1, 1, 1, 1, 1, 1, 1. What's a norm of that vector? It'd be 1 squared plus 1 squared plus 1 squared n times. It'd be n square root of. So the norm of that one vector is a square root of n, or the norm squared is n itself, by the way. Okay. So how would you calculate this projection to see that this actually is correct? And remember, the x bar vector is the vector, all of whose components are x bar the scalar. How would you calculate the projection of x onto 1 sub n? We'd take an inner product of those two vectors. We'd multiply by 1 sub n, the vector onto which we are projecting, and then we divide by a norm squared of that vector onto which we're projecting. Definition of projection from the previous section or two. All right. Hey, 1 sub n, the norm of that we just observed is n, so we pick up an n down here. And the reason the 1 sub n vector, the summing vector we called it, works is when you calculate this inner product, 1 sub n with x, maybe think dot product from linear algebra, you're going to take 1 times the first component of x plus 1 times the second component of x plus 1 times the last component of x. And you're going to add those up as you would in a dot product or an inner product in Rn. So what we get out of this inner product, if you like, we could express it in terms of thinking of these as matrices and a matrix product. 1 sub n transpose times x, so that we get the row times column stuff to work out as appropriate. We get the sum of the components of x. That norm in the denominator is n. You got the sum of the x sub i's. If vector x has components x1, x2, up through x sub n, you get the sum of those components divided by n. Well, that's x bar the scalar. So this quantity in parentheses is x bar the scalar. We're multiplying that by the vector 1 sub n. So this will give us the vector with components, x bar, x bar, x bar, and so forth. So it indeed is the vector x bar. Okay, when we look downstairs, we're going to be interested in expressing x bar in this particular form. Also, we saw in the last section, about the time we were doing the Gram-Schmidt stuff, when we introduced right triangles, we saw that the projection of y onto x is perpendicular to y minus the projection of y onto x. This is where we had a right triangle. The hypotenuse was x itself. These were the sides of that right triangle. So that's how we got the orthogonality in general. Here, we've got this particular type of projection. Here we can say x bar is perpendicular to x minus x bar, or x bar is perpendicular to, remember the centered counterpart was this vector x minus x bar. I assume these may be somewhat new to you. Let's scroll up. Yeah, the center counterpart x sub c was x minus x bar. So we're able to put a little bit of geometry in this statistics setting, which is, in my experience, that's a little bit unique. I mean, I can plot data points and get some geometric ideas. But here we're talking in terms of the Pythagorean theorem. You've got this orthogonality. Okay. So let's see. The fact that we know that x is a linear combination of x and x minus x bar, we can go through and express this orthogonality in terms of x squared equals norm of x squared equals the norm of x bar squared plus the norm of the centered counterpart of x, is x sub c squared. Pythagorean theorem. It's a right triangle. Let's write these things out in terms of components of those vectors. I'm fishing around here for some formulas. Here comes a variance downstream. So this is a plan. All right. Vector x, norm squared, that'd just be the sum of the squares of the components of x. We were denoting those as x sub i's. All right. X bar, the vector x bar, norm of squared, that'd be, well, it'd be n times x bar squared, kind of similar to what we had with a 1 sub n vector. It'd be x bar squared plus x bar squared plus x bar squared n times. So n x bar squared, x bar, the scalar here. All right, and x sub c had as its definition was vector x minus vector x bar. So the components of it will be x sub I minus x bar. X bar, of course, the scalar here. Okay, so if we take the Pythagorean theorem, geometric idea up here, gives us this particular formula here. This part reminds me of variance. If we'll divide through by n, in fact, divide both sides of this equation by n, we'll pick up a 1 over n in this term. Let's see, we'll divide by n here and just lose that coefficient of n. That'll leave us with an x bar squared here. We'll have a 1 over n in this other term. If you'll solve that for this piece, then you're left with that sum, x sub I minus x bar quantity squared divided by n equals a sum of the x sub I squared over n minus x bar squared. If x1 through x sub n was data from a population, need a population because we've done some division by n here in this slide in particular to speak of variance. But if this was data from a population, then we have the variance is given by this particular formula. We saw it above. X bar and mu are the same when we sample. Well, we don't sample when we have the entire population of data. So we can rewrite this as this is the population variance, sigma squared. This, well, don't have a particular name for it, sum of data points squared divided by n. And over here, we get the parameter mu. It's a good point, good time to point out. I've created a supplement to this section of formula. So we were just looking at, let's see, sigma squared variance is sum of x sub I minus mu, quantity squared over n. That's exactly what we had. We had mu to be the sum of the x sub i's over n. That's the same as x bar, whether we have a population parameter or a sample statistic. Throw the lingo around a wee bit. So same thing if we have the population, so we pick up a mu here. And this was the sigma squared quantity. So that's where this little formula comes from. A familiar formula, I've claimed. This is familiar to you if you've had the misfortune maybe of having to compute variances from a table of data by hand can be tedious. This formula is not as bad as some formulas if people still compute these things by hand. But here's a formula that expresses the variance in terms of some of the other parameters, the mean and the data points squared divided by n summed up. And remember, this is equivalent to, I mean, not that the pieces correspond precisely, but this is equivalent to that vector equation given here, which ultimately results from the Pythagorean theorem. Now, what really makes us tick is the way we defined the centered counterpart x sub c. That's what really made this geometric property synchronize so well with this little formula from statistics. Some other things we can do, the definitions here, not well motivated until we do some computations with them. For x, a vector in Rn, an n vector, the scaled vector denoted s sub c, x sub s, is x sub s equals square root of n minus 1 times x divided by the norm of the centered counterpart of x. Okay, I can define what they want. A couple of observations. One of them this n minus 1 thing must be the perspective of samples, and the rest of the stuff we'll see n minus 1 instead of n's. So they're thinking samples from a population. They've taken x and divided by the norm of the centered counterpart. All right, we'll see in a second why this is thought of as a scaled vector. It has some nice properties in terms of standard deviations and variances. The centered and scaled vector, x sub cs, is the square root of n minus 1 times, but this one looks a little less weird, x sub c, the centered counterpart of x, normalized. So they're taking a unit vector and multiplying it by this square root of n minus 1. So that's the centered and scaled vector. This process of creating the centered and scaled vector is called standardizing. We're defining the standard deviation. Okay, this ought to be the same thing we had upstairs from your previous experience, but here we're defining standard deviation of vector x. Remember, you're thinking of this single vector x as a vector containing a bunch of data points from a sample from now on in this section. The standard deviation of that vector x of data is the scalar quantity, s sub x, is the norm of the center counterpart of x divided by n minus 1 square root of. Okay, and we'll look at that here in a second in terms of components. And let me pop back over to my formula sheet. See, I had a bunch of population parameters at the top, some sample statistics listed secondly. Yeah, these are all could be interpreted in terms of pieces of a vector, right? The x sub i's could be pieces of a vector. And that's what we'll see when we elaborate on this in terms of components of x here shortly. But the standard deviation is defined to be the norm of x sub c divided by the scalar square root of n minus 1, and the variance is the square of that, as usual. And when you see the n minus 1s, you know they're thinking samples. All right, so let's take that standard deviation, that s sub x, which was defined to be the norm of x minus c, and divide it by square root of n minus 1 and see what we get. The centered vector, x sub c, that was the vector x minus x bar. To my formula sheet, just to give you something at your fingertips to refer to. Yeah, the center vector x sub c was x minus x bar. So x sub c has a components. First component, x1 minus x bar. Second component, x2 minus x bar, and so forth. So if we look at the components of this, square them, take a square root, that's how you calculate norms, we get this formula here. So standard deviation would be x1 minus x bar squared plus x2 minus x bar squared plus, and so forth. All right, that's the standard deviation. Let's take a peek at the formula that we had for standard deviation. Here it is right here. Sum of x sub I minus x bar squared divided by n minus 1, square root of the whole thing. Only difference is the square roots are written slightly differently, but equivalent. So this is the same kind of thing you have when you deal with a sample standard deviation for a data set, x1 through x sub n. Oh, and the variance, of course, is the same as a sample variance. Okay. Let's take the variance of this x sub s vector. The s sub s vector, that scaled vector above, bounce over here, I've got the scale vector on the formula sheet as well. Here we go. Scaled vector was defined as square root of n minus 1 times vector x divided by the norm of x sub c. That's their definition. Let's see what they were up to with that. So let's take the variance of that. It makes sense, right? You take a variance of a data set. You've got a data set. X vector is a vector of data. Okay, you've got these constants floating around in there, but anyhow, we'll see what happens. All right, so here's the very definition of x sub s. We want the variance of that. How did we take variance? Let's go to the formula sheet. We calculated variance of a vector x by taking the norm squared of the centered version of that vector x, the center counterpart, and dividing by n minus 1. So we ought to see a norm of some vector, whatever we're taking the variance of, some vector, center counterpart, norm of squared, divided by n minus 1. So we should see the norm of the center counterpart of this thing, squared, norm of the center counterpart of this thing, squared, divided by n minus 1. So that's our definition of variance. We just need to decipher what all this stuff means. Well, it shouldn't be that bad. It's just a computation. And let's see, center counterpart of this vector. Okay, here's the vector x. We'll find the vector. Here's the vector we're interested in, I should say. I shouldn't call it x because x stands for something else. But there's the vector we're interested in. We want the center counterpart of it. Okay. What we'll do then is find the average of this vector, the usual x bar style. Well, we've got this constant square root of n minus 1 divided by the norm of x sub c. That'll really just come along for the ride. And when you find the average of this, that'll just produce an x bar. Now, here we're looking at x and the x bar. These are both vectors, right? There's a vector, the x bar. There's a vector, the x. The other stuff, scalars. Those better be vectors because we're taking a norm of them, squared, and dividing by the n minus 1. Okay. Maybe to get to this second vector quantity a little more quickly. Hey, if I take the mean of ax as a vector, we get a times the mean of x. There's a little claim in terms of vectors as streamlines at. If you think how these things are computed, these are not at all surprising. All right, so we got some common stuff here. Hey, here's a square root of n minus 1, scalar multiple in both of these. We bring that outside the norm as an absolute value. It's a square root, so it's not negative. Don't need the absolute values. And to boot, it gets squared. So when you bring these square root of n minus 1s out, they get squared. They'll cancel with the n minus 1 down there, and we're done with the n minus 1 stuff. All right, we've got a norm of x sub c in the denominator of both of these. Bring that out, put it in the denominator, and then you're simply left with the x vector here minus the x bar vector here. So this reduces down to this quantity. Hey, x minus x bar, what was that? X minus x bar, that was first numbered thing on my formula sheet. X sub c was x minus x bar. Back to the notes. So what we get is x sub c in the numerator, or if you like, x sub c is x minus x bar in the denominator. Here was a formula we had, and this reduces down to 1. That's the reason they call it the scaled vector. It's a vector with variance 1. So in that sense, they've done some sort of, I want to say, use the term normalizing, some sort of scaling to some standard. If the variance is 1 and the standard deviation is also 1, reminding me of a standard normal distribution. Okay, so let's move on to more interesting data. Suppose you have a bunch of pairs, x sub I, y sub I, for I equals 1 to n. So we're dealing with, to use some of the math stats language, a discrete random variable pair, capital X, capital Y. But we're getting data points out here for I equals 1 to n, think x coordinate and y coordinate, with which we could associate a covariance and a correlation. Okay, these are the definitions from an introductory to statistics course. The covariance, maybe not quite done in our introduction to probability and statistics, but done in one that's slightly more sophisticated. Covariance is defined to be 1 over n minus 1, sum of x sub I minus x bar, y sub I minus y bar. Just a recall comment from your statistics background. Correlations were computed in terms of this covariance divided by a product of standard deviations. These are formulas you encounter in an introductory stats class in terms of covariance and correlation. When you do a linear correlation, this pops up. All right. Let's, with an eye towards that, let's define for x and y in vectors, think of them as vectors of data, the sample covariance. It's going to divide by n minus 1 as we did upstairs. Sample covariance between these is, by our definition, the inner product of x minus x bar and y minus y bar. Those are x sub c and y sub c, if you like, divided by n minus 1. There's our definition. That ought to be the same thing we just had up here. Up here in terms of dealing with just data points. All right, so what we've accomplished, if we've done this correctly, is we've taken this summation stuff and really replaced it with an inner product. All right, so covariance is given this definition. Let's see if we can't find another way to compute it. I guess is what we're up to at this stage. Let's introduce the summing vector, the 1 sub n. Then we can write, okay, it's going to require some patience on everybody's part. We can write x minus x bar, vector x minus, well, the only thing you can subtract from a vector is a vector, so this must be the vector x bar, equals vector x minus x bar times 1 sub n. Well, 1 sub n is a vector, so this x bar, come on now, that little x bar must be a scalar. So we've got a scalar coefficient of a vector. Just unfortunate notation, but it is implied from the context whether we're dealing with x bar the scalar like we are on the right-hand side, or x bar the vector like we are on the left-hand side. And similarly for the y vectors. Yes, being careful that we're using x bar and y bar for both scalars and vectors. It's clear from the context. Okay, covariance, let's see, was defined in terms of this from what's upstairs. We just saw that we can express the x bar vector, say, as x bar scalar times 1 sub n vector. And the 1 sub n vector is the vector of all n. So when you multiply by x bar, you can get the vector of all x bars. So certainly that's correct. So we can do a little substitution for the x minus x bar and y minus y bar, introducing the 1 sub n vector. Okay, here you got a inner product, and we've got linear combinations in each components, each entry of that linear product. Well, you know the properties, they're unsurprising, of inner products. So we can take this and expand it out a bit using the linearity properties of inner product. Let's not go into vulgar detail, but use those linearity properties. It will expand out like this. Okay. Here, for this inner product, we've got a vector with all components, x bar the scalar. Here we've got a vector whose components are y1, y2, and so forth. So when we take the inner product, or if you like, dot product, we get x bar times y sub 1 plus x bar times y sub 2, and so forth. So we get a sum from I equals 1 to n of x bar, the scalar, times y sub I, the data point. Over here, same type of thing, except now the constant is the y bar, and the thing that varies will be the components of the x. All right, over here, we've got a vector of all x bars and a vector of all y bars, the scalar, and we'll take a dot product of those, inner product, and we'll get x bar times y bar, first component, plus x bar times y bar, second component, plus n times we'll get x bar, y bar. Okay. Hey, I tell you what. Let's get a 1 over n in this summation. So I want to see a sum from I equals 1 to n of y sub I over n. So I'm just going to divide by n. If I multiply by n at the same time, then the book's balanced. So we're taking the x bar outside of the summation, introducing an n here, and a 1 over n there, so I can simplify that summation. And doing the same thing with this sum. We'll bring the y bar outside, there it is. Put an n on the outside and a 1 over n on the inside of that sum. Distribution says you haven't done anything wrong. I'll leave the first and last terms the same. Hey, then this summation is y bar, this summation is x bar, and we can rewrite this as given here. And now some things simplify. We've got inner product of x and y minus n x bar y bar minus another n x bar y bar plus an n x bar y bar. A couple of these cancel, and we can express that covariance in terms of inner products and x bars and y bars as given here. If we took the covariance of x with itself, okay, similar type thing. Here was our definition of covariance, properties of inner products, similar manipulations to what we have above, except there's some more similarities with what's going on here. We'd end up with the covariance of x with itself. That'd be the sum from I equals 1 to n of x sub I minus x bar squared over n minus 1. Well, that's just, I can hop to the formula sheet and confirm, that's just the variance of x. So the covariance of x with itself is the variance of x. I'm no statistician, but that rings a distant bell. Some properties of covariance are as follows. We'll go through, we actually just proved the third one. We used an x instead of a y. We're taking vectors, x, y, and z in vectors, and a is a scalar. The covariance of a times 1 sub n with y is 0. We'll think what happens here. This is a constant. This is the vector a n times. So when we do a covariance there, we'll get 0. We'll see when we go through the computations. If we take a scalar multiple of x, the covariance of ax with y, that scalar will come outside, a times the covariance of x and y. A piece of cake, probably not very complicated with just the data formulas, but a piece of cake for us because we can use matrix methods and vector methods to establish this stuff. Covariance of y with itself is the variance of y. Yeah, we just showed that. Covariance of x plus z with y is the covariance of x with y plus the covariance of z with y. A linearity type behavior in that first component. If we were to take x plus y, covariance of that with y itself, it's looking for the difference in these two. So we've taken z to be y. In this, we'll get the covariance of x with y plus the covariance of y with itself. covariance of y with itself is the variance of y. So that's how this second formula differs from the first. Oh, also, if we did adding a constant up here, replacing, then we'd have the covariance of, so we've taken z to be, the z parameter to be a vector that's constants a throughout for its components. We get the covariance of x plus y plus the covariance of a 1 sub n times y, and we see in part 1 that that's 0. So that's where the fourth part comes from. Let's take a look at proofs of 1 and 2. If I can find them, here they are. Let's go back to the beginning of this. All right, so let's go through and prove these. Like I said, super straightforward. Here's how we calculated covariance. So the formula we had was exactly this. It was x sub c, y sub c, inner product divided by n minus 1, if you like. All right, let's take the covariance of this constant vector with y. Okay, that'll give us a y minus y bar in that second entry. A1 sub n minus its mean. Well, if you average a constant a, you get a constant a. So that produces the same vector here, a vector of those constants. And when we take the difference, that gives us 0. Inner product of 0 with anything is 0. So that's how the first one follows. Total piece of cake using the vector properties. Next, we want to take that vector in the first component and multiply it by an a. Okay. Still using the usual formula. So we'll need the average, the mean AX bar, the average of AX. Of course, that would just be the sum of the components. That'd be a times x sub I divided by n. I can bring the a outside that summation, and that gives us AX bar. So we mentioned something along these lines earlier. Then we're getting out of this covariance of AX with y. By definition, we use this. We just saw AX bar is AX bar, if you will. Hey, we've got an A we can factor out here. The inner products behaved in a linear way. We can bring that scalar A outside. Bring that scalar A outside. Linearity of inner products, what makes this work. And now we're left with x minus x bar, inner product with y minus y bar over n minus 1. Hey, that is the covariance of xy. So that scalar gets outside by the linearity of the inner product. And like I said, we've already done part 3 in the notes. Notes. Okay. Another definition of correlation. Again, we should see the same kind of formulas you're familiar with from data analysis, but we're going to define for vectors x and y the correlation between those two vectors, the components of those vectors. Correlation between x and y is defined as the covariance of x sub cs and y sub cs. So maybe go back and take a peek at what those were. That was the centered and scaled vectors. So to the formula sheet, centered and scaled, x sub cs was the centered vector normalized with this square root of n minus 1 factor up front. All right, so when we take the covariance of those, then we will get, I need my formula for covariance. Here's the center vector for x normalized. Here's the center vector for y normalized. I seem to be missing a square root of n minus 1 from both of these, but remember, when we calculated covariance, it's got, here it is, got an n minus 1 in the denominator. Okay, well, we picked up a square root of n minus 1. If you'll look at how these are computed from the formula sheet, so we've picked up a square root of n minus 1 from this first component and the second component, bring them both out, linearity of inner product, produces an n minus 1 in the numerator to cancel with the n minus 1 in the denominator, and it ultimately becomes this after simplifying. Then We can also bring the x sub c and y sub c out, linearity of the inner product again, and you're left with correlation being defined as the inner product of the center vector x, centered counterpart vector x sub c, and the center counterpart of y, vector y sub c. That inner product divided by those norms. That should sound quite familiar. Back in the previous section, when we looked at angles between vectors, we got things like this for cosines. Remember cosine of theta, where theta is the angle between two vectors, was the inner product divided by the product of the norms. It inspired us for defining the angle between vectors. So this correlation thing, it's cosine of some angle. Hey, cosines of angles, they're between -1 and 1. So indeed, as you expect, the correlation coefficient here is between -1 and 1, as correlation should be. Gentle describes correlation as a measure of the extent to which the vectors point in the same direction. Yeah, it's definitely got something to do with the angle between some vectors. It's the center vector, it's centered counterpart vectors, x sub c and y sub c. It's not x and y themselves, as we see here. But we do have correlation between -1 and 1. And let's see, I promised to try to link this back to some formulas you've seen before. We're close. Correlation between x and y, we defined it like this. All right. Let's see, let's take that denominator and play with it. I'm trying to get out something. We play with it a little bit, then we get, let's put an n-1 out here and an n-1 under each of these. They're under the square root, so actually this n-1 cancels with these two n-1s, square rooted. So we haven't changed anything. We want to do that because we can say then, hey, the norm squared of the center counterpart divided by n-1, that's the variance, right? Back to my formula sheet and variance. Yeah, variance was x sub c norm squared divided by n-1. That's exactly what we've got for both x and y. So this first quantity is the variance of x. The second quantity is the variance of y. We can take these centered vectors x sub c and y sub c and express those in terms of x and x bar vectors, if you like, and get something of this form, and recognize that, hey, this inner product divided by n-1, that's the covariance of x with y, right? Let's jump back to the formula supplement. I'm looking for covariance of x with y. Yeah, here it is. X minus x bar, inner product with y minus y bar over n-1. So that's what happened with the numerator and the n-1 part of the denominator to get us a covariance. So we get correlation related to covariance and the variance of the constituent parts in this particular sense. Were we to take the correlation of ax with y, so we've multiplied all of the data in this x vector by scalar a, how's that going to affect the correlation? Well, not much, it turns out. Possibly familiar with this. We'll take our formula for correlation. Let's see, here it is from the previous one. We'll take the centered counterpart of ax, center counterpart of the second one, y, inner product of those, and then divide by the norms of those centered counterparts. Okay. So centered counterparts, we'll get, if we expand the x one out, say, we'll have ax minus ax bar, which is ax bar. You know what I mean? We did this computation above. Downstairs, we'll have ax minus ax bar, norm of for the norm of the centered counterpart, so we can get something like this. We've got a common multiple of A here. We could bring that out front. Linearity of the inner product. We're getting lots of mileage out of linearity of the inner product. In the denominator, we can also bring an A outside of this norm. Remember, it comes outside of the norm as an absolute value, though. So we can have absolute value of A out there. And hey, X minus X bar, that's the centered counterpart, X sub C. Here it is down there again. And what we've got here is an inner product of X sub C with Y sub C divided by the product of their norms. Well, that was a correlation of X and Y. And up front, we've got A divided by the absolute value of A. Now, unless A is 0, so this is not allowed for A equals 0, then we simply got the A divided by A. That'd be the sine of A, SIGN sine of A. If A is positive, then this is 1. If A is negative, then this is negative 1, the sine of A. So multiplying one of the sets of data by a positive constant doesn't change the correlation at all. Multiply it by a negative constant doesn't change the magnitude of the correlation, but changes the sign of the correlation. So there's how that manipulation of data affects correlations. So there's a way to take those formulas you have from introduction to data analysis, introductory statistics, and code them in terms of vectors and inner products, and even give a little geometry to some of the formulas. Okay, that'll take care of chapter 2. On to chapter 3. The bulk of the material for the course is in chapter 3, and the sections in chapter 3, at least the first few of them, are pretty lengthy. So we'll try to get you videos for those. Have a nice day.